This video is about calculating pH. You should already be able to identify acids and bases based on their hydrogens, hydroxides, or Bronsted-Lowry theory, and describe the pH scale as acids being low and bases being higher in the pH scale. But at the end of this video, you should also be able to calculate the concentration of ions or the pH of any strong acid or base. So the question of the video is, according to this diagram on the right, how much more acidic is your lower stomach at its most acidic versus your upper stomach and your saliva? So if you look at your lower stomach at its most acidic, it was 1.5. The upper stomach at its most acidic is 4, and the saliva is 6.5. So we want to know, what does that really mean? We can tell that the lower stomach is more acidic, but how much more acidic is it? So let's talk about the ion product constant. If you write the equilibrium expression for water's ionization, water forms H3O plus ions and hydroxide ions in equal quantity. So for every water particle that gains a hydrogen from another one, that means that hydroxide is left over. And that's why it actually evens out. This doesn't happen very often, which is why water doesn't conduct on its own, but there are trace ions for both. So if we wrote the Kc, it would be hydronium ions times hydroxide ions. Remember, it's products divided by reactants, and there are no reactants because water is a pure liquid. So you're only having concentration in the ions there. This is known as the Kw, or the K, equilibrium constant for water. And there's actually a value for this at 25 degrees. The Kw is 1 times 10 to the minus 14th. You don't have to memorize it. It's written on the reference table. And it's also pretty convenient because if you remember, the pH scale only goes up to 14. So look at that. There's the 14. A little foreshadow of what we're going to see. So if we calculate the hydronium and hydroxide concentrations, we would just plug these values in for the Kc. So the Kc is 1 times 10 to the minus 14th equals hydronium times hydroxide. And in order to solve for 1, we would just square root both sides because they're both going to be the same value. So if we square root it or raise to the half power, we get a value of 1 times 10 to the minus 7th. That's a very, very small concentration of hydronium ions or hydroxide ions. Very, very, very small. And they're both the same. So what's the pH of the water, and how do you know? The pH is just a shortcut. It's the power of that hydrogen concentration. So the power is 7, right? So the P scales are pretty easy. It's just the value of how many hydrogens you have and the power of that hydrogen. So what it tells you to do is take the negative log of a quantity, in this case hydrogen ions. So a pH would be the power or the negative log of the hydronium, because a log takes away the 10 and the negative takes away the negative exponent. So if you were looking at some other P values, you'll see POHs, which would be the negative log of OH. Turns out pH and POH are both add up to 14, which was the highest the Kw comes to, remember? And these values are all in the reference table, so you should look those up. So if you multiply hydronium times hydroxide, you get to 1 times 10 to the minus 14th because those powers add up to 14, right? Remember when you're talking about scientific notation, if you multiply scientific notations, you really add the powers up. So those are the same rule, basically. So with pH and pOH, if the hydronium is 1 times 10 to the minus 3, that means the pH of the power is 3, because what you did in your head, which you didn't know you were doing, was you negated it, and you took the log, you took the 10 away, right? So if the hydronium is 10 to the minus 9, negate it, and take the 10 away, you just get 9. If the hydroxide is 1 times 10 to the minus 4, the pOH, or the power of the hydroxide, is, again, negate it and take away the 10, is 4. Or if the hydroxide is 1 times 10 to the minus 12, the pOH, the power of the hydroxide, is 12. Notice I colored these different because if the power of hydrogen is lower than 7, it's an acid. And if the power of hydrogen is higher than 7, it's a base. I think I actually colored these wrong. We'll get back to that in a little bit. Well, I'll talk about it now. Remember, pH and pOH is equal to 14. So if the pOH is 4, that means the pH is 14 minus 4, or 10. So this should actually be basic. And if the pOH is 12, that means the pH is the rest, or 2. And so that should actually be acidic. I messed those up. So using that rule, if the pH is 3, what's the pOH? 14 minus 3 is 11. Or if the pOH is 12, the pH is 14 minus 12, 2. So this is all about taking those powers down. So how do we measure pH? For less accurate measurements, if you want to just go through a little test, you might use litmus paper. If litmus is red and it turns the paper to blue, it's a basic substance. Its pH is higher than 8. If it's blue paper and it turns it to red, its pH is 5. So you need to use both blue and red papers, put them both into a substance that you don't know. And if both turn blue, it's basic, and if both turn red, it's acidic. If they just say their own colors, both red and blue, then it's neutral. And you can also use indicators such as phenolphthalein we used last year. If the phenolphthalein was colorless, then when it was an acid. If it's pink, it was a base, right? It changes color at 8. But there's a lot of different values that we can use. So you don't have to just use phenolphthalein where it's colorless before 8 and pink after 8. All these other, and there's hundreds of indicators, would tell you different things. I like the ones that double change, like thymol blue. It's red anything lower than 2. So that means a very extreme acid would be red. A weaker acid or something neutral will be yellow. And something that's basic is blue. So I think that's pretty cool. They also have universal indicators that change colors multiple times, like a rainbow of colors for each different pH. So we'll play around with some of those. But the best way to measure the pH is to use pH meters. So you might have like a digital strip or something like this that we have. We have a cool contraption that connects to our computers, to our calculators that plug in and measure the pH based on how well it conducts. Remember we said, if it's very conductive, it's a strong acid, and it can figure out how many ions are conducting and convert that to a pH for you, which is really neat. Earth also has a natural litmus. Hydrangeas are blue when the acidity of the soil is between 5 and 5.5, and red when the acidity is 6.5 to 7.5. And a mix of colors can be seen anywhere in between, which is actually counterintuitive because if you remember, this is an acid value and it's turning blue, so it's like the opposite of litmus. And this is a more basic value and it's turning red, so it's the opposite of litmus, but it is still cool that it changes color with the pH. You need to write this down. The strong acids that you need to know for the test are hydrochloric, hydrobromic, and hydroiodic, which are the halogen acids with the exception of HF because it's hydrogen bonded. And then your ic acids, or your 8 ions, nitrate, sulfate, phosphate, and perchlorate, become nitric acid, sulfuric acid, phosphoric acid, and perchloric acid. So the ones that have a lot of O's, or halogens, with the exception of HF, are really strong. And therefore they're strong electrolytes, they conduct electricity really well, they burn your skin, they taste really acidic, which means sour, and they're reacting with metals really, really strongly and vigorously. And for these, for as many acids you have, that's how many hydrogens you have. They completely dissociate. So if you put 1 molar acid in, you get 1 molar of hydrogen ions. If you put 2 molar of acid in, you get 2 molar of hydrogen ions. And so to calculate it, you just do a pH equals the negative log of that hydronium or acid concentration. It's pretty simple. So if the hydrogen concentration is 2.5 times 10 to the minus 3, we want to calculate the pH, we know the power is close to 3, but because the base, you can't just negate it and take the 10 away, there's a base number. Let's actually put it in our calculator. Negative log of 2.5 times 10 to the minus 3 is 2.6. Do you see how that 3 is close to 2.6, but this is a little bit more accurate? You're getting a little bit better, refined answer if you negative log it. If the HA is 3.5 times 10 to the minus 8, 8 is a good estimate, but if you negative log it, you get 7.46. Another little note about pHs. These values in the concentrations have 2 sig figs, right? 2.5 or 3.5. Your pHs have 2 decimal places. The pH sig figs start after the decimal because this 2 refers to the exponent, which is never part of the number anyway. So this 2 is kind of the exponent part. These 2 numbers after the decimal tell you how specific you are. So since I have 2 base numbers, I have 2 decimals. 2 base numbers, 2 decimals. Strong bases. The strong bases you need to know and you should write down are the soluble hydroxides, which if you remember from the beginning of the year are the alkali metals like potassium, sodium, lithium, and so on. And the heavier alkaline earth metals, calcium and barium ions. I just remember the A bases, the Ca, Ba. And that means, again, that they're going to dissociate completely. For every base, there's a hydroxide, or maybe 2 if there's calcium hydroxide and barium hydroxide. So if you put 2 molar of a base in, you get 2 hydroxides. If you put 3 molar of a base in, you get 3 molars of hydroxides, and so on. And so therefore, if you want to find their pHs, you're going to negative log their hydroxides and subtract from 14 because remember, hydroxides plus hydrogens become the 14 value total. So to do that, we know that the concentration of some hydroxyl metal is 1.5 times 10 to the minus 4. What is this pH? I can estimate that the pOH is 4, and therefore the pH is probably somewhere around 14 minus 4, which is 10. But if I actually want to figure it out, I'm going to do the negative log of that value and subtract it from 14. So I got 10.18. Remember again, since my base number had 1.5, 2 numbers, I have 2 decimals. Let's do it again. The concentration of the hydroxyl metal is 2.2 times 10 to the minus 13 molar. And so if I was to do this in my head, I would say that the POH is somewhere around 13 and the pH is somewhere around 14 minus 13, which is 1. But if I want to be more specific, I'm going to add 14 minus the negative log of that value and I get 1.34. So you can see how the exponent gives you an estimate, but it doesn't have any sig figs. If you want to have a perfect answer, you're going to do the negative log values. So think, what's another way of calculating the pH of 2.2 times 10 to the minus 13th? I don't have to do 14 minus the negative log. There might be some other way. What I would think to do is you could say the concentration of hydroxide times the concentration of hydronium is 1 times 10 to the minus 14th. So what I could do is to divide from 1 times 10 to the minus 14th, or the kW, and get the value of the hydrogens and negative log that. I think that's the longer way, but do you notice you get the same answer? So there's a couple of ways to calculate these, and this is why we come up with the pH square. Maybe take a picture of this or find it online or rewrite it in your notes and pause the video. But it's showing you that there's two ways to get each thing. So like I can go from hydrogen to POH by doing getting a hydroxide from dividing from 1 times 10 to the minus 14th and then negative logging it. Or I can get there by doing a 10 to the minus pH and then subtracting from 14. Right? So there's two ways to get each thing. Similarly, POH, if I want to get POH from hydrogens, I could go clockwise or counterclockwise through these calculations. So it's kind of nice to write this down a couple of times, get used to it. Well, we're using it in class. Back to the question of the video then, how much more acidic is one part than another? So if we go to the lower stomach, its value is 1.5. So that means its hydrogen concentration is 10 to the minus 1.5. Remember, it's the power of the hydrogens. And if I put my calculator, it fixes it for me to make it 3.2 times 10 to the minus 2 molar. Let's do that with the upper stomach. The upper stomach, its pH was around 4. So if its pH is 4, that means its hydrogen concentration is 10 to the minus 4 because this is the power. And that can be rewritten if you don't like how it looks there, 1 times 10 to the minus 4. What we can see is it's actually 100 times less acidic because it's off by 2 tenths, right? Or the lower stomach's times 10 more acidic, 100 times more acidic. Let's do that again with saliva. Saliva's value is somewhere around a pH of 6.5, that should say, sorry. And the hydrogen ion concentration is 10 to the minus 6.5, which if you put in your calculator, reorganizes it to 3.16 times 10 to the minus 7th. I knew it was the most neutral, but we can see that it's 1,000 times more less acidic than the upper stomach, and like 100,000 times, right? We're just looking at exponents here. I'm not really caring about the base number too much. But like, there's 5 differences between -2 and 7. So that means 5 zeros difference in those two values, right? Because these are exponential. So the lower stomach is roughly 100 times more acidic, and the upper stomach is roughly 100,000 times more acidic than the saliva. And so at this point, you should be able to calculate concentration of ions or the pH of any strong acid or base.